How can we possibly know what's miles and miles beneath our feet? I mean, we've never drilled to the Earth's center. We haven't even come close. And yet somehow we have these incredibly detailed maps of its interior. So what's the secret? Well, it turns out we just have to listen very, very carefully. Let's find out how. Our guide for this journey is a really groundbreaking paper from 1978 called Q of the Earth. The scientists behind this, Anderson and Hart, didn't need some massive drill. Nope. They used the entire planet as their own personal laboratory, listening to its vibrations to figure out what it's really made of. You see, their mission was to figure out how the Earth rings. It's a great analogy. When a massive earthquake happens, it sends these powerful shock waves ripping through the entire globe, making it vibrate just like a giant bell that's been struck. And by measuring the quality of that ring, they could figure out what the stuff that the sound was traveling through was actually like. Okay, so how in the world do you measure the quality of a planet's ring? Well, that brings us to the core concept of this entire study, a really simple but powerful property that scientists just call Q. Now, what is Q? It stands for quality factor, and it's really just a scientific way of measuring how squishy something is. It tells us how fast a material soaks up energy and stops vibrating. So a high Q means the vibration lasts for a long time. A low Q means it dies out almost instantly. The best way to think about it is this. Picture a big steel bell. You strike it, and you get that long, beautiful ring. That's a high Q material. It just doesn't absorb the energy very well. Now, imagine hitting a lump of wet clay. All you get is a dull thud as the vibration just vanishes. That's a low Q material. So what Anderson and Hart were doing was basically making a high and low Q map of the entire Earth. But to do this, they couldn't just stick a single microphone on the ground. They had to combine clues from all the different ways our planet vibrates after an earthquake. Let's take a look at their toolkit. Their toolkit had three main things. First, they listened to body waves, which are the waves that dive deep through the Earth's interior. Then they analyzed surface waves, which are the ones that just ripple along the crust. And, my personal favorite, they studied normal modes. That's when the entire Earth vibrates together like one giant humming sphere. Each one of these clues revealed a different piece of the puzzle. All right, so with these tools ready to go, they started their journey heading down from the surface towards the core. And right away, they confirmed something really fascinating just beneath our feet. They found that the outermost layer, the lithosphere, where the tectonic plates are, is a high Q zone. It's rigid and brittle, just like that bell. But right underneath it, they discovered a really distinct low Q layer. This zone is softer, weaker, almost squishy. It's like finding a layer of incredibly thick honey hiding underneath a hard candy shell. It's a place that just soaks up vibrations. But that squishy layer doesn't last forever. As you go deeper into the lower mantle, the Q value starts to climb up again. The pressure down there is just immense, and it squeezes the rock, making it way more rigid and a lot less squishy. The planet, you could say, starts to get its ring back. Now for the deepest part of the journey. Because when the scientists started probing the very center of the Earth, the core, that's when they found the biggest surprises of all. Get this contrast. The liquid outer core has an extremely high Q. It's not squishy at all for certain types of waves. But the solid inner core, it had a surprisingly low Q. A solid ball of iron was behaving like our lump of clay, just absorbing a massive amount of energy. Now, that was a puzzle. And this perfectly captures their main conclusion about the core. They wrote, the source of the required bulk dissipation probably resides in the inner core. In other words, they were saying, look, we're seeing this mysterious energy loss in our data, and it can't be explained by the mantle. The culprit has to be the inner core itself. So now they had all these clues. A rigid shell, a soft layer underneath, a mantle that gets stiffer and stiffer, and this really weird absorbent inner core. The final step was to put it all together into one single model that could explain everything they were seeing. And this is it. This is the big payoff, a model they named SL8. This single line you see on the graph represents their complete profile of the Earth's squishiness, or its Q value, at every single depth. It is literally a map of the planet's interior, built just by listening to it vibrate. So you can see the whole journey we just took right here on this graph. It kicks off with the high Q crust up at the top, and then, look, it takes that sharp dip into that low Q squishy layer. From there, it's a long, steady climb in rigidity all the way through the mantle, right before it hits that energy-absorbing inner core at the bottom. And to put a single number on it all, they calculated that the average Q for the entire mantle, all 1,800 miles of it, was 235. This one number represents the overall ring of the mantle, neatly balancing out the super rigid, high Q parts with that critical, low Q soft layer. So this is just a fascinating piece of scientific detective work. But why does mapping out the planet's squishiness actually matter? What does it really tell us about the world that we live on up here? Well, that squishy, low Q layer they so carefully mapped out, that's what we now call the asthenosphere. And it is, without a doubt, one of the most important features of our planet. It acts like a lubricating layer that allows the massive, rigid tectonic plates to slowly slide around on top of it. Without that layer, there'd be no plate tectonics, no continents drifting, no mountain ranges being built, and a whole lot fewer earthquakes. This research really helped nail down the physical reason for how our world works. And you have to remember, this all came from data gathered way back in 1978. It's just such a powerful reminder that our planet is constantly humming and vibrating with information about its deepest, darkest secrets. It really makes you wonder, doesn't it? As our listening tools get more and more sensitive, what else is it waiting to tell us?